Great. As I said, my name's Alfred Bresnik. I've been involved with TIMS from the start. There were two of us graduates from the University of New South Wales who were approached the by the professor who came up with this teaching concept, and we have for about 30 years commercialized this system. So I'll first of all give you an explanation as to what is the teaching purpose, what is the teaching method, and why we use this method within telecommunications courses. So the first point to state is say that, well, let me talk about the company. So before I talk about this modeling system. So our company is Imona Instruments. We're based here in Sydney, Australia. We're only a few kilometres from the centre of downtown Sydney, and actually we're located opposite the University of Sydney, which is the oldest university in Australia, and also power users of the TIMS system. So let me give you the background to the TIMS system that you can see behind me. So some time ago, a lecturer of Communication Systems 1 and Communication Systems 2 at the University of New South Wales, Mr. Tim Hooper, was put in charge of the communications course and the comms lab. And what he saw at that time was that students were spending quite a bit of their time building electronic circuits or writing software code before doing the communications experiments. This he didn't like because he said he had a lot of topics to cover and only a limited amount of time. So he didn't want his students building electronic circuits and debugging them before doing the communications theory experiment, or writing code and debugging it before doing the communications experiment. So he looked around, and what he saw mainly was either software simulation, or just as I'll use this book, or what we call single panel trainers, where one trainer might be analog modulation, let's say AM, single sideband, double sideband. Another panel trainer might be FM and phase modulation. Another panel trainer might be sampling and reconstruction, and so on. And he said these panel trainers are very interesting. The students can see signals, but so what? They adjust a few parameters. The students aren't involved in the theory that he was teaching. So he tried a number of different concepts. And TIMS was the result of this teaching method, which deeply integrated the mathematics and theory that he's presenting in his lectures with the actual practical labs, so that students would get a better understanding and feel for this mathematics and theory associated with telecommunications. More than that, he was also looking for a system where which was again more modeling based, so that it could expand. So as telecommunications theory develops over time, experiments can be added without buying a whole new set of equipment. So this is the background to where TIMS came from and why TIMS came into existence. Before I show you Tim Hooper's teaching solution, we'll take a step back, a step above, and say that what Tim Hooper was particularly interested in was the fact that technology changes over time, as we've all seen, but the principles, the theory remains the same. And what that means is, the original probably long-distance communication was smoke signals, a bit like on-off ping. But seriously, the first real electronic communications was implemented with valves. And then technology changed to transistors. And then technology changed to ICs and today FPGAs and SDR. But what's common between the valves, the transistors, and the SDR? What is common is what Tim Hooper wanted to teach the students. So the engineer would have the underpinning and fundamental knowledge, theory knowledge, to apply this communications theory to whatever technology. And here is what the theory is. This is the block diagrams, the common language, the international language of telecommunications. So it's that theory that Tim Hooper wanted to focus on, and not so much the implementation at this stage. Later subjects, HF, UHF circuits, or microwave circuits, and so on, these are all different implementations of this theory that was being taught in subjects like Communication Systems 1 and Communication Systems 2. Because whatever the technology might be in the future, whether it's quantum computing or optical transistors or whatever, the theory that is being implemented is still the same. So what was Tim Hooper's solution? Well, his point was, he said, I'm already teaching students the mathematics and the theory, and all of this mathematics and theory is always expressed as block diagrams. So if you open any telecommunications textbook, any telecommunications paper almost, there'll always be block diagrams, because this is how communications engineers make sense of and understand what is happening. So Tim Hooper's solution was to say, in the block diagram, where there's a multiplier, which you can see up there, to have a real electronic multiplier block. Where there's an adder, to have a real electronic adder. So the TIMS system is exactly what I've just shown you, is many, many blocks which relate to that block diagram, and that's how the students build the experiments, by looking at the block diagram, doing calculations with the mathematics, and building the experiment. So each experiment is built by the students, step by step, in an engineering way, adjustments made and so on, so that the student can see what happens to those signals. So, as you can see here, there are blocks for signal source, adder, multiplier, phase shifter, blocks from the block diagram, and there are the TIMS modules, as we call them. And notice one important thing. No module is an experiment by itself. Every experiment is built by following the block diagram. The block diagram is the instruction on how to build that experiment, that modulation scheme, or that demodulation scheme. So how difficult will this be for students to have to build each experiment? Well, Tim Hooper thought about this and developed the system in such a way that students can pick up modules and in most cases, start to use them without having to read the user manuals, because if TIMS follows very strict conventions. For example, here you can see inputs are on the left, outputs are on the right. Analog level signals, bipolar signals, are yellow, and you can see from the system behind me and here, digital signals are red. So immediately there's this convention. Another important point you can see in the slide and here in the webcam, notice that none of the knobs have any scale markings. This is intentional because we don't want students to set to 9 o'clock to 12 o'clock. We want the student to actually use use the measuring instruments to adjust the amplitude, the phase, the frequency, according to the theory that they have calculated, or maybe the simulation, the MATLAB or LabVIEW results that they've got, they adjust. So the student actually builds the experiment. So the positive side of this is, as professors have told me when they've taken TIMS or tried TIMS, they said, you know, Alfred, we understood what you said. We patched together an experiment, but it didn't look right. It wasn't working, but we remembered that you said build the experiment step by step, adjusting each parameter, and then the experiment falls out. So the students actually learn these engineering concepts of adjusting, making adjustments, looking at signals, making decisions. Does this look right? Is this the value that I expect? Is this the value that was predicted? So the students are building the experiment. So if you have, the downside is, if you have lazy students who haven't done any preparation and just willy-nilly patch together an experiment, the resulting waveforms will be valid mathematically, but may not be useful in a communications concept. And what I mean there, just as I can demonstrate this, is, for example, if you patch together something simple like AM and you don't care about the amplitudes and phases and frequencies, you may have the result that is the trigonometric result, the formulaic result that's correct, but you may have overmodulation, undermodulation, or different offsets. So the results are correct mathematically, but they're not useful. So you need to adjust it so that you have 100% modulation, so that you're not clipping, and that the appropriate message frequencies and passband frequencies are selected, and so on. So this gives you a very quick overview of where TIMS came from, what the teaching method and the philosophy behind the teaching method is, and how students actually use the system. So with that, I'm almost finished just this first part, and I'll ask for any questions. So you might look at this and say, well, okay, you're talking about some simple blocks. What can you actually do? Well, this slide shows you above in the white boxes is the transmission model, the message, encoding, modulation, channel, demodulation, decoding, and receive message. And under each of those, you can see the different encoding schemes that TIMS can implement. And under modulation, have a look. TIMS can do from the simplest modulation, which we would probably say is double sideband suppressed carrier, the multiplication of two signals, right through to the latest OFDM, 4G, 5G concepts. So TIMS covers a very, very broad range of experiments. What does this mean to you, the lecturer? This means that you look at your curriculum, you look at your course, and you can now choose those experiments that match your curriculum, those experiments that you want students to experience and to learn from. And not only does TIMS allow you to pick and choose the experiments, TIMS allows you to choose how deeply you want to go. You want the students to explore those experiments. You want the students just to qualitatively look at different waveforms, compare them, or do you want the students to go much deeper quantitatively, to make signal to noise measurements, bit error rate measurements, coding gain measurements? So TIMS allows you in one axis to choose the experiments, and on the other axis, TIMS allows you to go to different depths for each experiment, obviously matching the time that you have for your lab classes. So this covers the first leg of this presentation. So please let me know. Do you have any questions at this point? Before the next step, I'll actually do some demonstrations and show you these modules in action. Do you have any questions? Please let me know. Am I speaking too fast? Is it does it all make sense? So, any questions?
Yes, thank you very much. Is Alex here, lecturer from communication engineering courses and signal processing courses at RMIT. Thank you very much for the presentation. It's very, I know a little bit about the teams. Just a little bit myself. I've been finishing my um, undergraduate and postgrad studies at RMIT Melbourne. And my background is communication engineering. And when I'm telling you this one, because I was working as a tutor, a laboratory demonstrator in Melbourne, RMIT Melbourne, before I came here to RMIT Vietnam. And I remember that was a long time ago, maybe 10 years or maybe a little bit 15 years ago. I worked with teams. I remember when I was a lab demonstration for the communication engineering courses in Melbourne, I used Teams. It was a long time ago. I remember there was a modules that you presented, and I can see you have a lot of modules here. I would like to ask you about the FM modulation. Most likely you have here, but I'm running the course here, and we have some AM modulation and FM modulation and digital communication. We're running 3 experiments. So I would like to maybe a little bit later to ask you more about the modules that you have it in, because I can see that you have a lot of modules there, and to see that which are the mostly useful modules for my courses, so that maybe a little bit later I would like to ask you more questions. Thank you.
Okay, fine. I will just I'll interrupt my flow just to address your FM question, for example. So because TIMS is a modeling system, we can actually implement FM in 2 different ways, both narrowband and wideband FM. We can implement FM with a VCO, the simplest way, or we can implement FM using the harmonic multiplier technique, where we have bandpass filters and work at 33 kilohertz and then 100 kilohertz and so on. So with TIMS, it depends how deeply do you want to go into the FM experiments. So you can do simple FM experiments or more complex FM experiments. And what I would answer you is, yes, we have a list of modules here. I'll just show you quickly. So there. So there's a list of modules. But as I said, no module is an experiment. What's more relevant is, let me go back here, are the actual experiments. So in your position in the first pass, unless you're really familiar with the TIMS experiments where you can tell us, I want this module, this module, this module, it probably makes more sense for you to tick the boxes here of the experiments you're interested in. And we can then tell you what's the minimum combination of modules you need to implement those experiments, so that we can then work in and iterate to get to a compromise of the experiments you need and the budget and the time you have to implement the experiments. So I would prefer not to give you module experiment tables where you have to work out, I want this experiment, I need these modules. You just give us the experiments you're interested in, and we'll then tell you the modules that we can work there, and that works much faster. So so if that answers okay, I will go to the back to the presentation and do the practical.
Yes, thank you, because you have a lot of modules, and we would like to have that modules that we make in the experiment. So because we have an introduction, we have many courses. We have at this stage running communication engineering 1, which is introduction to communication engineering, and we have 2 AM experiments that I'm doing at this stage, and 1 with FM, and we have 1 with digital communication. And plus, I would like to just a little bit more add that in signal processing also, I'm teaching that course. I'm a course coordinator there, and there we have also some experiments that I think we can use TIMS for FIR filter. For example, we have FIR filter experiment, and also signal and spectra. So that's introduction. The students, they're learning a signal spectra, and after that going to doing an experiment with FIR filter. And that is also, I'm pretty sure I can see that what I looked at, you have a lot of modules which can be used for signal processing. Thank you.
Look, I will, after this stage, one of the topics I'll cover is I'll introduce, yes, the FIR and spectra and so on. There is a whole lab manual we have, which is some 300 pages, which is focused specifically on signals and systems experiments. So again, out of those 16 experiments, you can choose the experiments, whether they're spectra, whether they're Fourier, complex numbers, convolution, or FIR or IR filters. But in everything we do, all those experiments, I'll show you later, but I'll just like to say now, everything we do is hardware, not simulation. So the FIR filters that students build, they actually build them from blocks, not DSP. They're actually adjusting the gains, the coefficients, and delays and summing junctions and so on. They actually do this by hand so they can see that these continuous time and discrete time structures that they're learning about, the Laplace and the Z transforms, are not just mathematical abstracts. They're actually real life signals that they can actually see on the oscilloscope. So I will cover that, but that's just a quick jump.
Thank you.
So now I'll come back. I'll quickly go through this. This will be just very brief. If it's too quick, let me know. But just to give you, because I've given you the background of how TIMS works on screen and by waving my arms around, now I'll show you the real system. So this is the TIMS system unit. In the top, we have, in these units, we have 12 slots for the plug-in modules that we were just talking about. In the bottom are all what we call the fixed modules, the modules we use most commonly, things such as DC signals or buffer amplifiers, or most importantly, our master signals. And let me show you the master signals. The first thing with the master signals is the blue waveform is what we call our fundamental message. It's a 2 kilohertz sine wave. Of course, we have audio oscillators, we have other signal sources, but this 2 kilohertz is synchronized to the other waveforms, including the red one, which is our passband signal. Our passband signal is 100 kilohertz. So all our modulation, AM, FM, MSK, OFDM, ultra-wideband, spread spectrum, frequency hop spread spectrum, all those analog and digital modulation schemes are all set at 100 kilohertz. And here you can see why. Because we want the student to see that passband signal. If we chose 1 megahertz or 100 megahertz or 1 gigahertz, the student would just see a block, wouldn't see anything. Is this valid? Yes, because TIMS is a modeling system. From the equations before, you saw omega C. Omega is 2 pi f. If f is 10 to the power of 5, 100 kilohertz, or 10 to the power of 10, the mathematics is the same. It's just scale. It doesn't matter. The fact that we're not using RF, real RF gigahertz frequencies to create these modulation schemes, theoretically, is of no consequence. So using simple patching leads, using simple instrumentation, the student can create all of these analog and digital modulation schemes and actually see what those modulated signals, what those passband signals look like on a standard oscilloscope and standard spectrum analyzer. So here with the inbuilt instrumentation, this is the TIMS 301C with the 2-channel inbuilt instrument. The 304C has a 4-channel PC instrument. But here you can see the blue is the 2 kilohertz message and the red is the 100 kilohertz. And most importantly, as I mentioned briefly, this 2 kilohertz message, the 8 kilohertz sampling signal and the 100 kilohertz signals are all synchronized. And what that means is this means synchronized in a telecommunications sense, not in a digital electronic sense. In telecommunications, synchronized means that the phase relationship between the signals is constant. If the phase relationship wasn't constant between these two signals, one would be triggered and the other one would be running. So we have these synchronized signals so that students see if it's AM or if it's FM or if it's a sample signal, sampled and reconstruction signal. What they see is, in the first instance, just basic textbook images. What you see in a textbook for an AM waveform is what the student will see on the oscilloscope, either the virtual scope or the real scope. So in the first instance, the students see what they see in textbooks. Then you can develop it further and put in an alternative message, which is not synchronized, and now the student will actually experience what synchronization actually means in telecommunications. So let me jump ahead and show you. So I'm taking the adder, which has 2 inputs, 1 output, and 2 control knobs. So any module can go in any slot and it's all hot swappable. So I can plug it in, pull it out in real time. So let me connect this 2 kilohertz message to 1 input, and I'll connect this variable DC, you see, down here, to the second input. So the output is 2 kilohertz sine plus DC. So you can see as I turn this knob, so there is an example of an adder being used. If I disconnect the DC, all I have is gain control of that message. And notice something else. We do this on purpose in different modules. Notice that the adder is inverting. So why do we do this? Because in telecommunications, when signals are transmitted down a coax cable or through the air, how does the engineer know what the original phase is? Phase inversion is very common. So we introduce some of these concepts, like inversion, like different, for example, the multiplier, I'll show you, different gain coefficients, because we want the student to actually look and think and measure and understand what's happening. So this is not just simple spoon feeding. This is the student thinking about, what does phase inversion mean? Is it an issue? In some modulation schemes, it doesn't matter. In others, it does. So it introduces these concepts to the students. So let me, for simplicity, take out the adder and I'll plug in this multiplier. You see the multiplier has 2 inputs and 1 output, and here this switch is coupling. where the inputs are either AC coupled or DC coupled. So I'll plug this in. So what I'll connect 2 kilohertz to one input. I'll connect 100 kilohertz to the other input. So I'm now multiplying 100 kilohertz with 2 kilohertz. And if I look, there's the correct trigonometric result for 2 kilohertz sine multiplied with 100 kilohertz sine. So in communications, this is not so much trigonometry, but referred to as double sideband suppressed carrier. Now, with the virtual instruments we include, we allow students to look at this important idea in telecommunications of the student constantly thinking time, frequency, time, frequency. So here we can switch, and here we can see the blue is the 2 kilohertz message. Here is the lower sideband, 100 minus 2, and here is the upper sideband, 100 plus 2. So notice when I have DC coupling, there's obviously a small DC offset that's coming through. And look, you can see here, see this suppressed carrier that's what? It's about 30, 35 dB down. That's because the small DC offsets are feeding through. If I AC couple and block the DC offsets, look what happens to that carrier. It's now 55 dB down. So you see, TIMS is not meant as an ideal system. These are real signals with DC offsets, bandwidth constraints, phase constraints, so the student can look and learn what are they actually looking at? What's the difference between DC coupling and AC coupling? And you can ask the student, measure these signals and have a look. Why is that happening? What's the DC? How much DC is there? And there's probably 3 or 4 millivolts of DC coming through. That's it. So this gives you an idea of using the TIMS modules. You can see how they use inputs and outputs and looking at waveforms, and looking at the instrumentation, the oscilloscope, and the measurements, and the time, and the frequency. So this covers a number of the concepts that I've included in session 1. Let's finish this session by using 2 modules to build an experiment. So let me disconnect everything. So I will now again take the adder, remembering that any module can be in any position in the rack, and they're all hot swappable. So for this adder, what I'll do is I'll take this 2 kilohertz message you see, and I'll put it to one input of the adder. The other adder input, I'll take variable DC, and I'll patch that into the second input. So here we can see the output of the adder is 2 kilohertz plus DC. I will now patch 2 kilohertz plus DC into the input of the multiplier. That's there. And now I'll patch 100 kilohertz into the other input of the multiplier. So we have 2 kilohertz message plus DC multiplied with 100 kilohertz gives us, well, an overmodulated AM. Why? Because I'm a bad student. I didn't adjust. I didn't measure the parameters to get the desired result. And notice that this, what you can see here and even on this scope, are real textbook-like images. So let's look at the spectrum. So here we can see the blue is the 2 kilohertz message. Then we have the lower sideband, 100 minus 2, the carrier, and the upper sideband. Now, let me just skip across and say, let's say the student sees this. So here's an AM signal that's being clipped. So in the time domain, this looks nice, it's flat, it's good. But why is clipping bad? Why in the mobile phone network, why do the base stations, why do the signals have to be adjusted to make sure there isn't clipping? Well, let's look at the spectrum. Aha, you see? What does clipping produce? Clipping produces a lot of harmonics and a lot of noise. So here is a very simple demonstration, even using old-fashioned AM, to show why is clipping bad. So if we go back to this point and I adjust, here you can see now we're generating. Now from the spectrum it looks a clean AM waveform, and there it is. So this shows you how with the TIMS experiment, you as the professor, as the lecturer, you can decide what additional concepts you want the students to be exposed to. So you don't have to just follow our lab manuals, of which we have some 5,000 pages of lab manuals. You can take our experiments and say, well, this is good, but I want to edit it and I want to add other aspects that are important in my program. That's why, as I said before, you can choose the experiments that match your curriculum, you can choose how deeply you want to go, and you can choose what variations, how you want to customize those experiments to suit your students and to suit your curriculum. Next, let's look quickly at, very quickly, at a very interesting idea of recovery. So let me adjust this so it's reasonable. So I'm passing the AM signal through a precision rectifier. If I now pass this AM signal instead through a diode and through an RC low-pass filter, look what we see. We get the recovered message, but you see the ripple in the recovered signal? Is this a mistake? Is this an error? Let's look at the spectrum and we'll see. So there's the 2 kilohertz message, and we can see because we're using an RC filter, you can see from the roll-off that it's passing some 100 kilohertz components. So it makes sense. So now we're introducing the concept of an RC filter compared to a 5th order filter. Let's use a 5th order filter instead. And I'll just quickly patch this across. And look. So why don't we see 100 kilohertz ripple? Because look, at 100 kilohertz, the roll-off of this filter has completely suppressed the 100 kilohertz component. So here is a simple demonstration of showing the student very quickly and very easily what does it mean to have a first order filter, a simple RC, compared to a fifth order filter? So this is an RC, the filter. So when the students have been calculating those roll-offs, now they can actually see in the time and the frequency domain what this means. Okay, do you have any questions on this practical side that I've just been talking about? No?
Yeah, just a comment is it's very good because you can see the students they can do, because basically what I'm doing now at this stage, I am using MATLAB and simulating the students to see this one. So having the teams, they can see the simulation. I think what in Melbourne doing, they're doing the simulation and also showing the students to building up and to compare those two, and they can see they have the simulation in MATLAB, and they're doing actually they use LabVIEW, but we're using MATLAB now, and they're using the teams, and they can compare and can see it. Basically, they can build it by themselves, the students, and they can see in the oscilloscope the same waveform what they do in the simulation. So I think doing this experiments, the students, they can see, feel, and they can see all these experiments. So that's pretty good. Thank you.
Look, your point is really valid. It's really important, because if you do now experiments like, for example, QAM or some phase where phases are involved, and the students do a simulation of that, the results they'll get will be mathematically perfect. But when they implement them on TIMS, they'll actually see real live signals, and they'll see that the signals using real electronics are not 100% mathematically perfect. There are little offsets. So you'll see other quadrature components and so on, and I can demonstrate that, so that the signal will never be 100% null. There will always be a small component because of the nonlinearities, because of the phase and frequency effects of real electronics. And another example is I'll just break this up and give a really good example that was given to me by two professors, one in Germany and one in America. They gave the students a tutorial question, so they must have been using the same sort of textbook, to design a front-end filter for a receiver. So they gave the students the signal, all the parameters of the transmitted signal and the channel. And one student came up and said, "Oh, look, I use MATLAB. I really, I understand it. And here's the optimum filter for the receiver." The professor says, and again, this happened twice. And the professors asked, "Oh, what's your result?" And the student says, "The optimum filter is a order 256 filter, because look at the great effect." And the professor said, "Oh, okay, you've understood the question, but so I'll give you 49% for your work so far. Now go to the lab and build me this filter, and I'll give you the rest of your marks." Because the simulation can go off and give perfect mathematical results, which are not always realizable. So doing what you're saying, allowing the student to do the simulations and then to look at real signals, is actually an added value. The student is learning a whole lot more about simulation and the real world. And this is what engineering is all about, isn't it?
Yes. Thank you. So I don't want to get ahead. Do you have any experiment or showing us for digital communication?
Yeah. If you look at the page 7 of our brochure, you can see here, as I go down, the digital communications. I will show you one I'll cover some of this, and then I'll do one very interesting spread spectrum experiment for you. But yes, if you look at page 7, it really depends what.
Yeah, Q and yeah. So basically, what I'm doing, also what we are doing, so the same like in Melbourne, we're doing QAM and PAM, and we are comparing. We're giving the students and to compare. They are doing a very big, well, they're doing one experiment, digital communication. This is in my course is Introduction to Communication Engineering.
Mm-hmm.
So the third experiment, it said the first one is like signal and spectra, just have a feeling they looking for the different type of signals, but the spectra, the second experiment, they're doing AM and FM, and the third one is a big experiment. They're using the digital communication, and they're using constellation diagrams.
Mm-hmm.
And we're giving them to compare and to see what is the difference with the PAM and QAM. And we're trying to do different levels. Yes, so that is also that's a big experiment. There's students for 4 weeks, and that's also important to learn the students about, because we have optical fiber communication. We're not giving any experiments, but we're doing for AM amplitude modulation, analog and the digital communication.
Mm-hmm.
So you have the amplitude modulation, and we have the digital communication one experiment. Yeah, thank you.
Look, in that list, really, it's up. The choice is quite enormous. From simple digital modulation, ASK, FSK, BPSK,
yes.
through to QAM, QPSK, through to multi-level, 4816 QAM, 4816 PSK, and then constant amplitude schemes like MSK, Pyron 4D QPSK, and so on. So yeah, there's a huge selection of digital modulation schemes, which again you can choose based on what modules you originally have, or what additional areas you want to explore. So I will cover some of this, including the fiber optics, just in the next couple of minutes. So at this point, before I start looking at some of the individual modules and experiments, I just want to give you a quick overview of the manuals, just in the next minute or two. So user manuals, like this basic user manual, I want to show you. I assume, let me just zoom in a little more. So the advanced modules and these basic modules user manuals all follow this principle. So if you open any of our user manuals, such as this one here, or what I'm showing in the screen, the user manuals, there's the title, the name of the module. There's always a short description of what this thing does. There's a description of the front panel labels, then a block diagram for that, and then there's use, how the module is used, and basic specifications. So in this example, I've shown you essentially what every TIMS user manual looks like. It all follows this pattern. Next, we have 3 different kinds of experiments. So just let me quickly demonstrate these. First, we call the lab sheet experiments. These are single sheet experiments. They are, in some universities, they're used by students, and the professor just says, here's the essence of an experiment. Now develop the experiment to do it. Or most often, the lab sheet experiments are used by professors when they get TIMS to see, I'm interested in QAM. How do I do QAM? Or how do I do BPSK? Or how do I do simple spread spectrum? So instead of working through a 10 or 20 page experiment, we have in 2 sheets. For example, sampling. Here, this is sampling experiment. what modules are used, what are the block diagrams, what are the basic principles, and what's the patching diagram. So these are lab sheet experiments. So you can see there's about 160 of these experiments. They all follow this one sheet that gets you into the experiment instantly. So lab sheet experiments are very good for you to quickly see, how do I implement experiment? So it saves you time trying to work out. Next, we have what we call student text experiments. So these are the more detailed experiments. These are typically, can be anything from 10 to 50-page labs. Obviously, the 50-page ones are quite complex spread spectrum and experiments. So with these, if I come down to the start of the lab, let me go quickly. Okay, so here's amplitude modulation. Let me zoom in a bit. So here you can see the sections on the amplitude modulation experiment. So then we cover the modules that are used, some preparation.
Sorry. Can you please go back? I saw you have some tutorial questions. So what are those tutorial questions?
These. So if I go back to the previous experiment.
Yeah, tutorial questions. So what are those tutorial questions? That is, okay.
They're
Yes,
examples of explorative, just to further probe the student, for the student after they've completed the lab to see if they can answer these questions, if they understood what they just did.
I see. Okay, that's good. Thank you.
So first with the lab sheet, the single sheet experiments. Then we have some. Honestly, I've lost count. It's some 12 volumes of these detailed experiments, and they are all available to you. The experiments are listed in a separate document where you can go through and see all the different experiments of the many volumes that are in essence summarized in that transmission model. So last, let me go back to another type of experiment we call explorative experiments, where there isn't as much guidance given to the student. There's the core guidance on the block diagram and setting up the experiment, but then in these experiments, they're open a lot more for the student to explore and to investigate different aspects of these experiments, and lots of opportunity for the student to record their findings. And so there are student versions of these experiments, and then there are the professor versions, which are 2 or 3 times longer, which have all the sample waveforms and all the results. So these are the 3 different kinds of experiments that we cover. And the reason I wanted to introduce these is now I'm going to go into this second session, because we're 1 hour into the presentation, where I'm going to start covering some of these individual topics. So let me switch to, let me just go back very quickly to this presentation and just finish some slides. So I showed you using an adder and multiplier using AM. We looked at the time and the frequency domains. We looked at filter effects. We looked at distortion and overmodulation. So what I've shown you up till now, I wanted to get to this slide to show you that with TIMS, it's not just these, modulation, demodulation. It's everything in between. Where we have the transmitter, you see a noisy channel, so we model it So we can control the amount of noise. We can control the channel bandwidth. And then we have the receiver. And then we have instrumentation such as bit error rate. But if I go back to the noisy channel, it's at that point that the student measures and calculates the signal to noise ratios. So we don't have an SNR instrument. We have a true RMS voltmeter, or the virtual instrument, which measures true RMS voltage. So the student actually measures the noise coming through the channel, the noise voltage. They measure the signal voltage. And from that, they do the 20 log calculation to see where does this dB thing, number, come from. So they can see the eye diagrams, they can see when they're adding noise, so they can relate what this dB thing means. So if a student comes up and says, oh, I think I measured 100 dB signal to noise, a student who's actually experienced this will look and go, I don't think so. That doesn't make sense. So it gives students that feeling for where the dB comes from, because they're actually involved in doing it. And similarly for bit error rate, we don't have a BER instrument. We use an exclusive OR gate, as you can see in that diagram, where we compare the received data with a local version of that data, and they are synchronized up using the sliding window correlator. It works very quickly and very simply, so that the student can now plot waterfall curves. So in the same way that they can plot waterfall curves in a MATLAB simulation, they can now do that same QAM or MSK experiment and plot the waterfall curves, and now they can compare the MATLAB results or the Simulink results with the real electronic signals. And what they'll see is that the curves follow, but there are differences. And now they can think, why is there a difference between the real signal and the simulated signal? So this sort of finishes up this first section of TIMS and the TIMS experiment capabilities. So now, if there are no further questions, I will jump to my okay. So in this session 2 list, the virtual instrument I've shown you. Let's look at quickly at the first of these topics, which is software-defined radio. So the software-defined radio that TIMS implements is quite different to the many commonly available, either the small analog devices units or NI's USRP. We explode those complete SDR units where you have data in and RF out. We go to the heart of it in 2 ways. We have a module which runs GNU radio, but we operate at the heart, IQ in and IQ out. So this is at the very heart of the software-defined radio. And the software is actually on a USB. What we provide is we provide Linux Mint pre-installed with GNU radio pre-installed. So the student simply plugs this into their laptop or computer, they boot off this USB, and now they instantly have a Linux machine running. So there's no software to download or install or download from the internet. So we provide, our software-defined radio is the hardware and the software ready to run out of the box. So if I zoom in a bit closer, so the module, and you see this is not an SDR on its own. It uses other TIMS modules to build the communications experiment. Here's the software in the dongle. So now let me show you real examples. So here's one example, GNU radio modulator and TIMS hardware as the demodulator, showing students that SDR is not some abstract concept and it's all inside a magic box. What we have is, we have an audio oscillator as the message. We have the SDR module running GNU radio, which is the FM modulator. We use a TIMS module, this one, the quadrature utilities, which has two multipliers and an adder, and that makes the FM transmitter. So now we use TIMS modules, an adder, an RC, and a VCO to build a phase lock loop to recover that FM. So you see we're mixing SDR and hardware to show students that they're producing the same signals. And down here you can see in this slide a quick image of what this experiment looks like. So the transmitter is on this side with the GNU radio here running the SDR module, and here are the three modules creating the phase lock loop. So with this, I won't go into the same detail with the other examples, where we have TIMS hardware modulator and the GNU radio SDR is now the demodulator for a QAM signal, and so on. So this gives you a very, very quick overview, an insight into when we talk about SDR, how this is really focused as a very educational, hands-on SDR approach. Does that make sense? Any questions? Next.
Yes, thank you.
Great. Next, very quickly, we have a DSP module. This is our third generation module. It's based on TI's 6713 DSP and their DSK board, but we provide an add-on board which plugs in, which provides high-speed A to D and D to A, so that this is used in experiments such as convolutional decoding, trellis code demodulation, turbo coding, and OFDM. So that's where we use the TIMS DSP in these kinds of experiments. So and there I wanted to show you this. So you can see that the TIMS DSP is used together with other modules to create these, and I'll show you shortly further examples. This happens to be a convolutional coding and decoding experiment. So next, you mentioned fiber optics. TIMS implements a range of fiber optics experiments. The fiber optics experiments are summarized here. So first of all, the electrical, optical, electrical interfaces, both analog and digital signals, optical splitting and combining, bidirectional communication on a single fiber, and WDM. So what we have is, to show you, we have red transmitters, we have green transmitters. So you can see we're not using lasers here. We're teaching students the principles of optics. So this is not an industrial or a professional fiber optics lab with circulators and lasers and so on. Here the students can actually see the signals. So here we have an optical coupler, and you can see the fiber, the 1 millimeter polymer fiber we're using. So this coupler has two inputs, two outputs. So two optical signals can be mixed and go out the channel, or one channel signal can come in and the optical signals can be split. So we have these kinds of experiments. And of course, we have filters. So we have a red filter and green filter. So with these core building blocks and the other TIMS modules, these are the kinds of experiments that TIMS can implement in fiber optics.
Yes, so there's a question here. So you have an experiment on losses in optical fiber. That is if I understand correctly, a new fiber. So this is pretty new because I haven't seen this one from TIMS, the fiber optics one. The last one, you have losses in fiber optical systems. So this can be maybe another course in optical fiber as an elective, maybe a little bit later. It can be an optic fiber communication. And I'm interested in the last one. So is that you have an experiment losses in optical fiber in fiber optical systems or optical fiber system? Yeah. So you have that's all different experiments. Yeah. Fiber optical transmission, optical signal splitting. Yeah. A little bit, just briefly, can you talk about the losses in fiber optical systems? So what is this experiment? So what type of modules you have for this one?
The losses, we're using the transmitter, we're using these couplers, and also these bulkheads where the students, for example, connect these fibers in different orientations, so they can see that the orientation of the connection actually changes. So they're all quite quantitative, where the students are actually measuring and seeing the different performances. So remember, what we're operating in is these couplers. So this is our environment.
Yes.
The couplers, the polymer fibers, the bulkheads, and the receivers. Noting that the receivers have both have an analog output. I'm just looking to find the receiver.
Because we are presenting to the students how to calculate the power budget. So if they can use this experiment to calculate the power budget in optical fiber systems, so that you can simulate, yeah, the whole optical fiber system, yeah, with these modules.
This is a step. This isn't. We don't do these more advanced power budget calculations. Here, the student is looking at what the losses mean. Where do the losses come from? With this LED, bright LED environment. Okay, so yes, they make actual measurements on the original signal, the signal going through the system, and what are the losses in connections and so on. So the whole intention here is to introduce students to these concepts of why are there losses, bending losses, for example, and so on. So these are the different, broadly the topics where we're discovering, we have documented. So the fiber optics manual itself, I don't have it here, but I can send you a separate brochure which gives quite a detailed chapter, the chapter topics. The fiber optics manual itself is also some 300 pages of experiments covering this, and what we call the physics of fiber, polarization, as I said, bending losses, and different gratings and so on. So yes, we do cover those sort of concepts ready for the student before they go into the commercial fiber optics lab. So this is all the underpinning concepts.
Okay, thank you. Okay. Thank you.
Okay, the last one I'll cover in this section is expansion options, which are open to you, the professor or the student. So the first is a simple one, is an expansion rack, which adds another 12 slots and sits on top of the TIMS unit. So that's obviously used in more elaborate, much more advanced experiments. Most important is this project module, where we provide, when you purchase TIMS, you get access to our users-only downloads website. And there you have access to all TIMS manuals, including the project modules manual, which gives you all the dimensions and all the physical specifications for making these modules. And with that, you can either purchase this project module from us, or students as capstone projects, or professors sometimes as projects, can design their own circuit boards and make their own modules to use with TIMS. So TIMS really is an open-ended system. Some years ago, I did a survey of professors, and about 50% had created at least one module of their own. And I soon learned to ask the right question, which was, what was your area of research in your PhD? And it was some area of telecommunications. And most often the professors would create at least one module that would demonstrate some of those concepts that they were so familiar with from their own research. They would all say, oh, this is a really important area students should be exposed to. So TIMS truly is a modeling system and an open system, because you can absolutely make your own modules. So if we don't implement an experiment, if we don't have modules to create an experiment that you think is very important, that you want to expose students to, the system is open for you to do this. Next, just quickly, there is a large breadboard which has an inbuilt power supply and buffered inputs and outputs, so students can actually wire together circuits on the breadboard and interface them with the rest of the TIMS modules. So that covers these, the projects side of our experiments. So next, I'll just quickly move to okay. Okay. First of all, let me introduce these. No, I think to cover. Let me go through here. Okay. So this is what I was just talking about, projects. This happens to be a photo of a student from Sydney University who implemented, his thesis was to implement gold codes, which he designed in MATLAB, but then actually implemented them in TIMS to prove and measure their coding gains and so on to prove if they work. I'll quickly skip through this slide. There are lots of quotations from users on our website. We have we now have something like over 5,000 pages of experiments. I wanted to cover this. So sometimes we're asked, what does TIMS cover in wireless communications? Well, TIMS doesn't have a Zigbee trainer or a GSM or wideband CDMA or a 5G trainer. What we do is TIMS operates at the physical layer. From the OSI model, that physical layer and layer 1, what is at the heart of, what is the modulation scheme? For example, 4G systems, 5G systems would not function without OFDM. So what we introduce students to is the OFDM layer, that physical layer. What are the characteristics? How does it work? Why does it work? What are the characteristics? Or in IoT, we don't have an IoT trainer, but we go down to the physical layer and we look at the different modulation schemes that are used in IoT, whether it's ASK plus DSSS or and so on, or ultra wideband, and what are the different. So we're looking at those modulation schemes at that physical layer, so the students can see what is at the heart of that so-called wireless scheme and how it's functioning. So here you can see, for example, Bluetooth, and core of Bluetooth might be Pi4D-QPSK. So we don't have a Bluetooth point-to-point. We're looking at that physical layer, that what is the modulation scheme that actually makes that work. So this covers that aspect. The other aspect, which I just had on before, is, well, so what do we cover in 4G and 5G? So here we can see number of experiments, bit error rate measurement in 16 QAM modulation schemes as used in 4G mobile, and so on. So we're again looking at that physical layer. So here you can see examples of these experiments in 5G, the low density parity codes, LDPC, or the polar codes that are used in the systems, as well as something that we cover the OFDM, different aspects of OFDM. As you spoke earlier, we compare, for example, a QAM signal going through a multipath channel versus an OFDM signal going through a multipath channel. So we expand to that sort of level of at the physical layer of what's happening. So with our OFDM, if you just excuse me for a minute, I'll open another brochure that I didn't open previously. So our OFDM experiments, so we have, let me just skip up. We have 3 kinds of OFDM experiments. The first uses no DSP. We use 3 audio oscillators which are tuned orthogonally. So we have a 3 subcarrier OFDM. So the students can see, what's this DSP doing? What is all this IDFT stuff? So we actually break it down so the students can actually do simple experiments with the concepts of OFDM. And then our next level is OFDM using the DSP module that I just showed you previously. Again, the input is data, the outputs are I and Q, so we use TIMS modules to build this experiment. Below that is an example. So here, for example, is the multipath channel. For example, here you can see we have 4 paths. So each path the student can adjust the gain and the time delay, and actually then see the resultant effects, not just in the time domain or the frequency domain, but we also dig into the DSP at the receiver, and we show the students vector diagrams of the phase and amplitude of each subcarrier at the receiver. So as the students change the channel characteristics, they can see what's happening to each subcarrier and what this means, and hence apply equalization and then do bit error rate experiments on that OFDM signal going through a multipath channel. So that hopefully gives you a little bit of an idea of our range. And if you're more interested in these, we have a number of YouTube videos which actually go and demonstrate these OFDM experiments in some detail. So that's, let me see. So next, any questions before I move to the next? No? Okay, now I'm just going to quickly skip through because I want to cover these rather quickly and then do some more digital modulation experiments. So we do, for example, concepts such as frequency hop spread spectrum at, as I said, at 100 kilohertz, where the students can see these frequency hop signals. We have a whole range of CDMA and time hop spread spectrum experiments. Now the topic that we covered earlier, we have a number of modules to implement these signals and systems experiments. And these modules are actually come with software, and we have a control panel which controls the coefficient gains of those modules. So the students can set up, and let me just quickly show you. Here are the experiments we have that we mentioned previously for our signals and systems. There's Lab 1's Introduction to the Signal Systems modules. Number 2 is Special Signals, the Characteristics, Linearity and Non-Linearity. Chapter 4 is a lab on convolution. Then Integration, Correlation and Matched Filters. Exploring Complex Numbers and Exponentials. Fourier Series Analyzer. Again, the topic that you mentioned earlier. Spectrum analysis of signals. Now, continuous time structures, poles and zeros, where the students are actually build the Laplace structures, sampling and aliasing, A to D conversion. Now, again, the ones you mentioned, discrete time, FIR filters, and IIR. So what that means is...
Can you please go back a little bit? Sorry, a very short question. So I can see that you have, yes, a Fourier series analyzer. What we do, we're giving to the students periodic and aperiodic signal, and first they have to do Fourier series, yeah, the first thing for periodic signals, and we're doing, they do some simulation, and after that they do in Fourier transform, because Fourier transform can use for aperiodic signal also, and they're doing a chirp signal, for example, and they do some experiment. I guess you can have different signals to generate, yes? So you have periodic and aperiodic signals to be able to generate, yes?
Precisely. We provide in the module, in the control module, we provide an arbitrary signal generator. So we provide a few signals and a template, but you can program in the signals and load in the signals that you want. So you've got complete control over the types of signals you want the students to analyze.
Yeah. So box function. Yeah. Okay. Thank you very much. So you have here. Just can you stay just 1 second, please, back for the signal module, because that is another course I'm teaching, and we have 2 courses in signal processing. So, signal and characteristics, linear, nonlinear, convolution. Yes, you can do convolution in discrete time and continuous time. So we teach them continuous and discrete time. So we have a continuous time system. We have discrete time system. Just I'm telling you what we are in the curriculum. Complex number exponential, Fourier series analyzer, good spectrum analyzer, and signals, poles and zeros in Laplace domain. So we're doing mainly in Z plane.
Discrete time filters. The S-plane, the Laplace.
Okay. Getting starting analog to digital conversion, sampling, aliasing. Yes. Okay. Thank you very much. Thank you.
Okay.
Thank you.
So this software, I'll show you. I'll answer. I think you probably have some questions, so I'll answer some of these queries. So here is obviously the block diagram of a discrete time system. So what we're doing is each of these coefficients is what the software controls. All the rest is hardware. So it's from the computer screen that the student types in a value for that coefficient, and that gets transferred via USB into the module, and that's what it sets there. So the student actually builds that structure block by block. And this software, you see here, adjustable gains for each coefficient setting. That's what is shown. That's what happens up here. So we have actually one tab for each of those experiments you saw. So each of these experiments has its own tab. So whatever instrumentation, whatever different data or whatever parameters need to be measured or adjusted, or displayed, there's one tab there for each of those experiments, including, you see here, FIR filter. So here you see the Z plane, here, the unit circle, and if you can see, there are poles and zeros plotted. So when a student types in the coefficients, the poles and zeros that result from that are actually plotted in that unit circle. So if the student plots in coefficients where the poles go over the unit circle, the poles will be plotted outside the unit circle, and the student will obviously have an oscillator rather than a filter. And the student will see that in real time. So if they move the poles too close to the unit circle and the system is, there's a bit error in the system, they'll see it breaking into oscillation and settling and so on.
So yeah, we're looking for the stable or unstable systems. Yeah, that's very good, because the students, we give them a lot of calculation and they can see it on the, they can check it and they can see on the, using this experiment. Yeah,
they get visual, they get instantaneous feedback. And the other thing is we actually map our chapters, our labs, against a number of, actually here only 4, but we actually map against 8 different signals and systems textbooks. The most popular we hear of is Lathy, but then there's Oppenheimer and Zimmer and some others. So we actually provide
yeah, we're using, okay, can you Oppenheimer? Yeah, McClellan, yeah, McClellan up there also, we're using that one. We are McClellan up there, yeah, this one, McClellan DSP first. And yeah, we're using Oppenheimer signal system 124. Yeah, thank you.
Okay.
Yeah, thank you.
So there we're mapping. So that answers an early question that you had regarding signal systems. I'll now just very quickly go through.
Yeah, thank you.
You know, for example, MSK, OQPSK, Pion 4D, QPSK, where again the students actually see the real, signals in real time. These constant amplitude schemes. Ultra wideband. Again, we implement ultra wideband, but at 100 kilohertz. However, the pulses are exactly correct. So we are actually scaling. That's why TIMS is a modeling system. We are scaling these ultra wideband schemes down so the students can actually see the pulses instead of at the real commercial or industrial bandwidths. The OFDM we have covered. So, and the other one that we have covered is the teaching concept. So this document of 4G and 5G experiments sort of ties together where TIMS sits with the latest experiments. And what I have to point out is that when RMIT Melbourne first purchased TIMS, probably none of these experiments in the 4G and 5G document existed. And some of the modules.
Yeah, yes, of course. But, that is this latest one, yeah.
But all of these experiments can be implemented on RMIT Melbourne's TIMS systems. Because when we release new modules, they're all forward and backward compatible with the TIMS units that were purchased 10 or 20 years ago. So that's an important thing to remember. So even the first universities who purchased TIMS many, many years ago, University of Technology Sydney here and the Royal Military College in Canberra, they can all implement on their old TIMS systems the very latest experiments that we have released, because the TIMS units have not changed. We can maintain that compatibility. So that covers an overview of TIMS capabilities. Now, just in the time remaining, let me show you one example of a spread spectrum experiment, just to show you that for most people, spread spectrum is this quite complex difficult scheme. But if we break spread spectrum down to its core concepts, I can demonstrate direct sequence spread spectrum very quickly and easily. So let me pull this experiment apart that we had. I'll just move these modules. So for our spread spectrum, let me go to this waveform. Our message that we will modulate and demodulate, transmit by a spread spectrum will be a 2 kilohertz sine. Our spreading sequence will be this pseudo-random sequence, which we are clocking at 100 kilohertz. So if I look at the spectrum, so the blue line is the spectrum of our message, and the red is the spectrum of our spreading sequence. So to create this direct sequence spread spectrum, what I'm going to do is I'm going to multiply two kilohertz sine with the spreading sequence. So I have let me go back to time domain. So I'm going to multiply 2 kilohertz sine with the spreading sequence, and that gives me, in the time domain, a waveform like that. Now, I don't think anyone can tell you what a direct sequence spread spectrum waveform looks like in the time domain, but in the frequency domain, now we can see what our spread spectrum signal looks like.
Yes.
So now, let me demodulate this signal. I'm going to take this module, which is our quadrature utilities, because it has two independent multipliers and an independent adder. I'm just going to use this top multiplier. So I'm going to take the spread spectrum signal and put it to one input of the multiplier. I'm going to take the same sequence that I'm using as the spreading sequence. So I'm going to steal that to simplify the experiment. I'm going to steal that sequence, multiply it, and go to the time domain. So there's the sequence, there's the direct sequence spread spectrum, and there's the demodulated spread spectrum. Now you can see it has a lot of noise. If we go to the spectrum domain, here you can see there's a lot of noise.
Yes.
What I'm going to do now, and this you'll see, the next two steps will be quite fascinating. I'm going to take this and pass it through a low-pass filter. Now let me just go back here. So
it will be much clearer. Yes.
So our blue is the original message. The red is the recovered spread spectrum. What happens if I use a different sequence at the demodulator? This looks interesting. It's not measurable, But let's look at the spectrum. And let me zoom in. So do you see the red? If I go before the filter, there's our spread spectrum. If I go after the filter, obviously what we can see is whatever I'm tuning, this is a tunable low-pass filter.
Yes.
But what we're seeing is the noise. Watch what happens when I change it from a different sequence to the original sequence. So there you can see the red coming through, and the noise is now 55 more, 60 dB down. So with this simple demonstration, we can explain and show to students the way spread spectrum works is each, for example, cell phone, mobile phone, has a different code. And that's why if there are multiple phones in the same area, because they have different codes, they don't interfere with each other. And here is a simple demonstration of correct code, wrong code.
Yes.
Wrong code, correct code. And you can see that from that spectrum, from all those harmonics being transmitted, when you have the correct code, it falls into place. And this is the simplest of demonstrations of spread spectrum.
Yes.
So this is my my very quick digital modulation scheme. So even though it's more advanced, in a sense, it actually shows you that it's quite simple. And just to explain to you, when TIMS was first released, there was no interest in spread spectrum, but we did have this core experiment in the back of one of our lab manuals. And some 5 years after, 5 or 10 years later, we started being contacted by universities who are asking, tell me about this spread spectrum experiment, because now it had moved from the US military, from NATO, into the commercial world. So now universities wanted to start to demonstrate the principles of this new technology called spread spectrum. And the most important point is that when they purchased TIMS, they had no need for spread spectrum. Years later, they could implement it using the blocks that were included in the basic system. No new modules were required to implement a completely new modulation scheme because the building blocks were already there. So that again ties up with my explanation and my concept that TIMS is actually a modeling system, and it's up to how you wish to teach in terms of range of experiments and depth of experiments. TIMS gives you that capability. That's why TIMS is a true hardware modeling system. So with that, do you have any further questions?
Yeah, thank you very much for the presentation, and also for very interesting one. Well, at this stage, there's a lot of information. I can see there are a lot of capabilities using TIMS, and it would be definitely a very, very good addition. I know they're using already in RMIT Melbourne, and we are looking forward to have it at RMIT Vietnam also implementing. Well, it is up to the line manager. So, well, to see that, and also all the lecturers and other team members from communication engineering stream at RMIT Vietnam, we have building up some capabilities. And yes, it's very interesting. Thank you very much for the presentation. Thank you.
Great. Look,
We would like to add something. Thank you.
look.
I have a lot of questions, but at this stage I'm holding back because I want to have a little bit more study and looking into the different modules and different looking on the curriculum, looking on the different program curriculum, course curriculum, and we'll have maybe more questions later, definitely. Thank you.
Okay, look, something to help you if you're interested. We can provide a link to this document, which is called which covers exactly this area.
Yeah, thank you.
It starts with the experiment capabilities, but then it breaks up into different undergraduate courses and suggested subjects and labs for different analog and digital and signal processing courses. So if you're interested, we can provide you a link to this document, and that might be able to help you sort out.
Yeah. That would be very good. Thank you very much. Yeah, sorry, I stop now. For you, Hui, thank you.
No worries, Alex. Thanks, Alfred, for a very, very detailed and informative presentation. And actually, M1 Teams is not really new to us. MIT Melbourne has been using Teams probably for many years, and we know how good the system is and how flexible it is. I mean, can be used for in terms of both teaching and research in undergrad and postgrad level as well. So that's the reason why one of the main objectives of myself and the team here in Vietnam is to explore the possibility to deploy the system fully in Vietnam. I think, like you said, probably what might work well is that you probably give us a link to this document that you are sharing right now. We will discuss within the team, and we will tick all of the boxes. I mean, in terms of the lab experiments or whatever things that we think we want to do and plan to do in the future using the team system. And then we will seek your further recommendation in terms of what kind of the system we should build to match 100% what we want to do here, right? And probably you can give us some recommendation for future for expansion as well, because what I see is that you have a lot of add-on modules over there. Also, I want to explore the possibilities to use team system to teach remotely as well, and we also want to ensure that students can use the team system wherever and whenever they want and whenever they are available for it. I see that you have I think team 301C or 304, and it has a net team system as well, which can be used via the internet. So I think that should be highly feasible, but probably it is something that we can discuss further, not in this long enough seminar.
Yes, look, of course, let me, in a nutshell, what I've shown you today on TIMS, a student can do on the NetTIMS FreeWire system, where on screen they select modules, they patch them together, and the results they get are real live signals from the inbuilt oscilloscope and spectrum analyzer in real time. The difference is that up to 50 students can use one unit, and each student, because of the fast time share, each student is running their own unique experiment.
Yeah.
So
yeah, and it seems that you have two options as well. Yeah.
Yes.
I think the free Y, which I think you can do quite a lot of, probably about 30 or 40 something basic and advanced experiments, and then for the advanced one, then it seems that you can do up to 200 experiments as well, which is fantastic. Yeah, but need a lot of work. I mean, in terms of preparation and pre-wiring.
Exactly. I think you understand the system really well, so thank you very much for your explanation.
Yeah.
Okay. If and when you have time and you're interested in the NetTIMS, we can discuss that at another time. So.
Sure.
Great. Okay then.
All right. Yeah.
So with that,
Yeah,
So-
I would like. Yes, I would like to add also that I can see some very exciting capstone projects from this using Teams. Also, we can use it that one. So it is a multiverse or multi-purpose. So it is very interesting. Thank you. Very good. Thank you.
thanks for your comments. I appreciate that. That's how we see it. And we appreciate the fact that you also recognise the multi capabilities of this teaching platform. So with that, if there are no further questions, we've come up to time. So I would say thank you very much. I appreciate your time, your interest, and most of all your questions. Thank you.
Yeah. Thank you very much.
Thank
Alfred.
you very much.
Yeah. Keep in
Thank you.
touch.
Thank you very much. Thank you. Bye bye.
Thanks a lot.
So I
I hope-
think thank you very much. But before we end, can I have some action item here? What would be the next step for us here?
So, I mean, from our end, what we expect is that probably we get a link to the document that Alfred is sharing right now, so that we can basically tick on the boxes regarding all of the experiment using the team system that we would like to do or plan to use in the future. Then probably Peritech and Emona team will get back to us with some recommendation. What is the ideal team system that we should come up with for our learning, teaching, and research activity here, right? And then probably we will take the discussion from there. Yeah.
Okay.
Yes.
Okay. Great. Thank you very much.
All right. Thank you, Everest, for your sharing today. It's very nice, very informative. Can you please share to us the link to the training today as well, so that we can keep it as a document for the future training? Thank you.
Will do. Great. Thank you very much again, and
Thank you very much.
we'll be in touch. Thank you. Goodbye.
Okay. Thank you,
Thank you.
Everest. We're looking
Thank you.
forward
Bye-bye.
to
Thank
your
you.
reply.
Okay,
Thank you.
thank you.
Bye bye.
Bye-bye.
Thank you. Bye bye.
Bye-bye.
Thank you.
Bye.